Hey guys, alright, this is the second part to the transfer of forces and moments inverse dynamic tutorial. I noticed a couple of things from the last video. My hand and my shoulder was in the way a lot, so I apologize for that. Also, I said something incorrectly, that the force of gravity acts negatively in the horizontal. It does not. It acts negatively in the vertical. I'll also put a note on that video. So that's just important because you need to know that the horizontal is perpendicular to that. Also, another thing that I noticed is that my hand sort of blocks whatever I write. You know, it's kind of hard figuring out a good camera angle, so I'll just try to twist my arm, but it might make my writing a little more messier. Anyways, whatever. Let's get on with it. Okay, so last tutorial we calculated the moments. Sorry about that. Okay, we calculated the necessary forces and moments acting at the knee. Okay. So take a look. So we took everything that we knew, calculated forces and moments. So the forces were in the X 19.6 newtons and then 53.11 newtons with a net joint moment of 13.87, I believe. Okay, so how do we transfer this? Do we just simply, this is equal to, in the thigh segment, this is equal to 53, that's equal to 19.6? No. So these two segments, the thigh and the shank, are joined together at the knee, right? So when they come in contact, well, they don't actually necessarily come in contact, technically, due to, the cartilage and the fat pads. That kind of attenuates some force and prevents bone-on-bone contact. However, for this explanation, let's assume that they touch each other. This is a sort of, well, it's analogous and parallels ground reaction force, right? If I, take a step on the ground exerts an equal magnitude force in the opposite direction relative to my step, or when you compare it to my step. I step down, ground reaction force pushes back up. So it's just like this. And this whole process is, Newton's third law. So a ground reaction force is basically Newton's third law. Any force exerted has an equal and opposite reaction, especially when it comes in contact with another segment. So let's say, for example, during gait, they touch. Now the forces transfer equal in magnitude, but opposite in direction. Right? That's how you transfer them. Even the moment. It's going up. This is positive. This will be negative. So, remember, Newton's third law is used to transfer moments between segments, and you can work all your way up each different segment, all the way up to the arm. That's I sort of had a exam question like this. We had to calculate the forces at the ankle, work our way up to the knee, then up to the hip. Yes. So, it's not something uncommon that you, in advanced biomechanics, so you need to know this. Anyways, let's get right to it. Alright, so we have the same setup like last time, in which we have the forces here, which were transferred. So we have the knee joint and then the hip joint. So what do we need to do first? That's right. You guys get it by now. Define the coordinate system. Alright, so we will start by calculating the f of x, sum of forces in the x component, equals the mass multiplied by acceleration in the x. So the sum of forces in the x are unknown, h of x, plus our negative, right? Calculated as positive, however, when you transfer it over, it becomes negative, it's going left. The mass is given here as 8 kilograms, multiplied by acceleration is 1 in the x. Carry this over. So, h of x is equal to 27.6 newtons. Right? So, sum of forces in the y equals ma(y). So, forces acting in the vertical component we know is given to us as negative 53.11. Just as a little rule of thumb, I don't write negative 53.11 because the direction of the arrow is giving the direction to the magnitude, right? Which is defined by our coordinate system. Down is negative, so that's why I don't add in an extra negative. I mean, you can for clarification, but a negative arrow and a negative sign actually means positive, but let's just not get into that. Whatever you feel comfortable, just know the signs. So, h of y equal to, is minus mg, which is 8 times 9.81 minus 53.11 is equal to 8 times 3. Right? So carry all this over. H of y is equal to 155.59, and let me just make sure of that. Okay, so now we have solved for the forces acting at the hip. Now we can go ahead and solve for the net joint moment acting at the hip. I've sort of derived why we calculate moments and how to do it in part 1 of the video. So refer to that if you're confused. You can go ahead and say a moment. The sum of the moments is equal to the mass moment of inertia multiplied by the angular acceleration. And we know, so basically it's like this in reverse, equals the sum of forces multiplied by the perpendicular distances, this is basically a moment. I just broke it up. Alright, so mass moment of inertia is 2 multiplied by 5. Is equal to, now we're going to take into account the moments. So once again, it is very important to understand where your pivot is. Right now it's at the hip, right? So let's take into account gravity. Gravity acts pulling down, right? So if you pull down in the middle, it's creating a negative moment. So 78.48 multiplied by the perpendicular distance, since this is acting in the horizontal, gravity is acting in the vertical, right, straight down, perpendicular to its line of action, is the horizontal. So, and since we know it acts as the comm, we take the difference between the x coordinate of the comm and the x coordinate of the hip. So that is equal to 0.15 of the comm and the hip. That's 0.15. And remember, it's in meters, and we know this creates a negative moment. Plus 53 this also creates a negative moment, right? Whoops, ignore that bracket. And the perpendicular distance, since this is acting in the y, is x. So x from this is located at the knee. This force is located at the knee. So you take that whole difference, take the difference from the x coordinate of the knee and the x coordinate of the hip. This creates a negative. So plus 19.6, actually running out of space, so plus 19.6 times, alright, now look at this here. Since the segment is angled like this, and we have another force that's pushing it at the knee like so, creating a positive moment. It's causing it to angularly rotate up counterclockwise, right? And since it's acting in the horizontal, we know from the line of action, perpendicular distance is that. So it's the difference between the y coordinate of the knee and the hip. 1.5. Creates a positive moment, and then minus 13.87 plus net joint moment. Alright, so 10 is equal to so we know this is negative 1.77 minus minus 21.24 plus 2.94 minus 13.87 plus net joint moment. So isolate by carrying all of this over on that side. So net joint moment is equal to 53.94 Newton meter. Alright, so the most important thing here to remember is how to transfer your forces. So once calculated, once the forces at the joint is calculated at the other segment, know to use and understand why you're using Newton's third law and why it's applicable here. Because the two segments are touching each other at the joint. Therefore, when you transfer the forces, it's the reaction force that is taken into account. So opposite direction equal in magnitude. And then once we got that, we're able to calculate the forces and the moments acting at the hip. I believe that's everything. Yeah. So understand that the signs when calculating the moment, understand that we're adding in negatives because they're creating a negative moment, right? Not because it's pointing in the downward direction, right? For example, this is a negative force. However, it creates a positive moment. So when calculating the moments, we add this in as positive. Okay. So hope that was that clarified you guys any ambiguity you had, and I will see you soon.